Right. Okay, so in the previous part, we have looked at solving the steady diffusion equation in 1D when the boundary conditions are all zero. But in any practical problems, we need or we encounter situations where the boundary conditions are not zero. For example, in fluid flow problems, the velocity is not always zero. So if it is all zero, then the, there is not but there is nothing for us to solve, right? So okay, so we are going to look at how to solve the steady diffusion equation when the non-homogeneous Dirichlet boundary conditions are specified. Okay, so okay, we have the same PDE. Okay, we have the same PDE and the same domain from HL to HR. Now the difference is that instead of zero boundary conditions on both sides, we have non-zero boundary conditions. So on the left side, we have a value of UL, okay, which is non-zero, and UR on the right side, which is non-zero. Okay, so the PDE is the same. The only change is in the boundary conditions. Okay, so UL and UR are the specified values of the solution at the left and right boundaries. Now, in order to represent them both in a compact form, let's assume that there is a function g, okay, which gives us the values of UL and UR at HL and HR respectively. Okay, and we have our Dirichlet boundary gamma d. Okay, so on gamma d, there is a function g, okay, so which we know. So that gives us UL and UR. So this boundary condition is simplified to Ux equal to g of x and the Dirichlet boundary gamma d. Okay, so this is the only difference compared to the previous example where we had Ux equal to 0 at both ends. Now, okay, so we start from from this step of the weak form. Okay, so when we derive the weak form, so at some point we ended up here. So we start from this step because the remaining steps that come before this step are the same, whether the boundary condition is 0 or not. Okay, so that's why we start from here. And then, yeah, okay, so we are evaluating the terms at the respective boundaries. Okay, now we identify that the boundary conditions are not 0. Okay, so we have used boundary conditions. Okay, now we choose, if we don't choose the test function such that it vanishes on the boundary, then we end up with these two additional terms in the weak form, which makes it complicated. There are some methods that we can use to solve this problem when we assume test function such that it is not 0 on the Dirichlet boundary. Okay? But it leads to complications. In order to retain the test function that vanishes on the boundary, that is, if you choose the test function from the H10 space, then U no longer satisfies the non-homogeneous Dirichlet boundary condition. Remember, we have U equal to G on the Dirichlet boundary condition. So, if you choose U also from H10 space, then U no longer satisfies the non-homogeneous Dirichlet boundary condition. So, what do we do here? Okay. So, to fix this, what we do is we assume that U is a sum of, that is superposition of a function u bar which is in H10 space. That means u bar satisfies the homogeneous Dirichlet boundary condition. Okay, that means, so whatever we did in the previous part, like that when we solve the homogeneous Dirichlet boundary problem. So that is the solution that is U bar. On top of that, we have capital G. Capital G is the extra term which corresponds to the non-homogeneous Dirichlet boundary condition. Okay, so G is no longer G is not in H10 space, but it is in H1 space. Okay, so here in H1 space, the functions do not vanish on the boundary. Okay, so G is in the H1 space, and we know small g. From small g, we can calculate capital G. Okay, now by making use of this, like small u equal to u bar plus g, and okay, so by using this, what we can do is we can still take the test function in H10 space, and by doing so, we can remove these terms. Okay, so by doing so, we can remove these boundary terms because the test function vanishes on the Dirichlet boundary. Now, once we remove these terms, we are left with only two terms, one on the left side and one on the right side. Now, in this case, instead of u, we have u bar because we substitute u equal to u bar plus g, and the g term we take it to the right hand side. Okay, so it becomes minus mu dou w by dou x dou g by dou h, capital G by dou x. So okay, so when compared to the problem with the zero boundary conditions, okay, so we have one extra term here, and on the left hand side instead of u, we have u bar, okay, which satisfies the homogeneous Dirichlet boundary condition. Okay, whatever the non-zero boundary conditions we have, that we account through this term, extra term. Okay, now what does this extra term do? Okay, so how does it help us in accounting for the Dirichlet boundary conditions, that is non-zero Dirichlet boundary condition? Okay, so this extra term. Now, by following the discretization that we applied previously, so we discretize u bar, like u bar equal to nu. Similarly, we discretize g. Okay, so g is similar to u bar, we discretize. So, and then after rewriting it in compact form, we get ku equal to f and minus kg. Okay, capital this boldface G is the vector of degrees of freedom corresponding to G. Okay, so this extra term adds some non-zero contribution. Okay, so it gives some non-zero contribution to the force vector, effectively modifying the force vector, accounting for the values coming from the Dirichlet boundary conditions. Now, let's see how this works in practice. Okay, so we go back to our previous example where we split the domain into 5. Okay, we have 5 nodes, 4 elements, and we know that u1 and u2 are specified. Okay, so we know that from G. Okay, and this is our global assembled mass stiffness matrix. Okay, and this is our original force vector, global force vector, and this is our extra term, and this is our k. K is exactly the same, and G, like we can write G or we can write U, it doesn't matter much. So we know U1 and U5 from G. Okay, so if you want to write, you can write G1 and G5. It doesn't make much difference. Okay, so U1 equal to G1, U5 equal to G5. So we know those values. Okay, now, so what we do? So we multiply the stiffness matrix with the known values of U1 and U5 and subtract that contribution from the global force vector. Okay, since we have only two values and in general we have only few values, it doesn't really make much sense and it becomes computationally like inefficient if you multiply the global whole stiffness matrix with the whole like G vector. So what we do, we do this step where we take the corresponding column, like for u1 the corresponding column is u1. Okay, and multiply it with u1 and then subtract it. For u5, we take the corresponding column, which is the last column, and multiply it with u5 and subtract it. In this way, the computations become efficient. So we don't, okay, and we subtract, and we take only those columns for which the solution is specified, for which which are on the boundary. Okay, so in a we slightly modify our example, okay, to account for non-zero boundary condition. So the same example, mu equal to 1, f equal to 1, same domain. Instead of 0, 0, now we have 1 and 2 on the left and right sides. And for this problem, the unitary solution is this. Okay. And after applying the boundary condition, okay, so we know u1, so we multiply this, and we know u5, and then we apply this. Okay, after simplifying, okay, once we take u1 equal to 1, u5 equal to 2, and then multiply the columns and then subtract and simplify. This is our final that effective global force vector after applying boundary conditions. So this is how, okay, as you can see, the values in the global force vector have changed for non-zero, for the problem with the non-zero digital boundary conditions. Okay, this is how we incorporate the effect of non-zero digital boundary condition. This is the same principle in like what we do in the, okay, in the case of other methods as well. Okay, so now after applying the boundary conditions, we can eliminate the known degrees of freedom by removing the corresponding rows and columns, and we end up with the reduced matrix in terms of E2, E3, E5, which are the unknowns. Then we solve for it, we get the solution. Again, here the note that the solution should be different because the problem is different. Okay, and then we can plot the solution. Now it is no longer 0, 0 on the ends. So on the left hand, the value is 1. On the right hand, the value is 2. Okay, it should satisfy the boundary condition. Okay, so how to implement this in MATLAB or Octave? Okay, so since we have already implemented it for the previous case where the solution, the boundary conditions are zeros. Okay, so this is our code. Okay, so I'm going to modify this to accommodate the non-zero boundary conditions. Okay, so here I'm going to create an array solution specified. Okay, I'm going to create this of same size as the solution, and in this, okay, I'm going to populate. Okay, so for the first node, for the first degree of freedom, the value is 1. And for the last node, for the last degree of freedom, which is total DOF equal to 2. Okay. And then our loop over elements and calculating the element stiffness matrix and assembling the element stiffness and element force vector into global quantities, it remains exactly the same. Okay, here we have the global force and global stiffness matrix. But before we solve, we have to apply the Dirichlet boundary conditions. Okay, so what we do here? Okay, so here we loop over the fixed DOF. We know what DOFs are fixed from the DOF fixed array. Okay, so in this case it is 2. But if we have a problem in 2 dimensions for Navier-Stokes, we can have 100 degrees of freedom. So looping over all of them is the best strategy to automate the code. So what do we need to do? We need to subtract from the global force vector. And what do we need to subtract? We need to take the column corresponding to this div from the global stiffness matrix. Okay, so we extract all the rows corresponding to this column. Okay, that means we extract that column and we multiply it with the specified value of the corresponding degree of freedom. Okay, so by doing this, we are applying this step, okay, over a for loop for all the degrees of freedom. So after the for loop, we should see these values in the global force vector. And while we are in this loop, we also populate the solution vector with this. Okay, for plotting, we need all the solutions. We need to have the correct ones. Okay, now if we check here, and the other steps, that is this step for solving the matrix system of equation is the same. We don't need to change anything. And for plotting, we need to change the Edgear solution. Trust the Edgear solution is different. Okay. So I keep the old one, and then the new one is 0.5 x plus 2. Okay, this is the one. Okay, minus half x square plus half x plus 2. Okay, minus half x. Okay, now let's see. Okay, something is wrong. 1, 2 is 0. Okay. So if something goes wrong, you can easily check here. Okay, so something is not added up. So before we apply the boundary conditions, this is fine. But after we apply the boundary conditions, only the first one is correct, but the last one is not correct. Okay, something is wrong. Okay, I'm glad we have this bug, so we can fix it. Okay, no. If something is going wrong, then you can check what is going on just by printing. Okay. So DOS 1, DOS 2. 2 is not correct. Okay, so that's not right. So the mistake here is, okay, so I have this, okay, but that's not DYF. DYF is this one. Okay, DYF is, okay, now it should work fine. Okay, right. So here DYFs are 1 and 5, not 1 and 2. Okay, after fixing this, our solution matches. And now from here we change the number of elements and the solution should automatically take care of all the rest. Okay, so now this is the solution for 10 elements and we can have 100 elements. Okay, now this should work. Right, okay, so that is how we solve PDEs using finite element method. Okay, so the important steps, again, just to reiterate, the important step is in implementing the finite element method is to derive, okay, going back to derive the weak form starting from the PDE using the residual of the PDE and the weighted residual statement. Okay, so once we have the weak form, we discretize it by approximating the solution and the test function. Okay, so after we have the discretized form, we split the domain into number of elements, and then so we can split the integral over those elements. Okay, and then for each element we can evaluate the integral as the stiffness matrix. For example, like if we have a two-noded element, then we have two basis functions that are non-zero, and by calculating their shapes and their derivatives, and we can integrate it exactly, we get the expression. This is our element stiffness matrix. Okay, so that's the theory, and in terms of implementation, we need to prepare arrays for assembling the element stiffness matrices into the global element stiffness matrix and element force vector into the global force vector. Okay, and then if we have non-zero boundary conditions, we need to account for them through these extra terms that modify the global force vector. Okay, so this is the basically, so this is the essence of the finite element method, like how we apply the finite element method in practice to any problem. So if we have other PDEs, so the stiffness the element stiffness matrix would be different. Okay, but the procedure for assembling, the procedure for applying the boundary conditions, and the discretization would be exactly the same. Okay, so you will see it. You will try to, you will be able to connect it once you solve more problems. For example, in the next lesson, we are going to solve the advection diffusion equation using the finite element method. Okay, so if you have any questions, please post, okay, in the comment section. I hope you find this lesson, this series useful. Okay, if you have any feedback, please let me know. I will incorporate it. I will try to improve the lessons. Thank you.